Hello once again, class, and welcome to another mock lecture. Today we're going to be tackling the law of cosines. We're going to start off here with an example. So two boats set sail with bearings of 52 degrees and 121 degrees, traveling at 20 miles per hour and 14 miles per hour respectively. Find the approximate distance between the two boats after 1.5 hours. So first things first, we're going to need to draw a picture of the situation. So here we go, right? The first boat, right, at a 52 degree bearing has a speed of 20 miles per hour. The second boat at a bearing of 121 degrees is traveling at 14 miles per hour. And we need to figure out the distance between them. So we don't know what this is. And in fact, we actually don't know what the other two distances are either. We actually don't really know much about this particular problem. The first thing we should do is tackle what are these distances here, right? How can we figure this out? Well, luckily, we know their speed. And from physics, we know that distance is equal to rate times time. So that means that this length here is 20 times 1.5, which is 30 miles. And this one here is 14 times 1.5, so we're going to get 21 miles. Okay, so we have this situation, and we should probably also figure out what this angle is because we can. One of the things we can do is notice that if we subtract away the 52 degree angle from the 121 degree angle, we're going to get that interior angle of the triangle here, which is 69 degrees. So if you notice, we have a side angle side situation, right? A side angle side case. So let's go and review the 4 different cases that we have for solvable oblique triangles. Now, if you recall, these last 2 here are covered by the law of sines, which means that side angle side and side side side, we're going to need to know the law of cosines for. So that's what we're going to figure out. What is the law of cosines? Wait, no, the law of cosines. Okay, so first thing we're going to do is derive the law of cosines. Just like we did with law of sines, I don't like to just give us the formula. I like this to derive, right? Figure out where it comes from. So I've drawn just a standard labeling of a triangle here, and I'm going to make A the point 0, 0. So I'm going to make it coincident with 0, 0. In fact, I'm going to make that whole base B just coincident with the x-axis. Now, and it should be noted, I could actually do this for any of the vertices, right? I could make B 0, 0, right? I could make C 0, 0. It's going to change what the base, quote unquote, of this triangle is going to be. But I just decided, without loss of generality, we're going to let B be the base. I think that's appropriate. Okay, now here's the thing. We know this is 0, 0. If the whole length is B, then this is the point C, is the point B 0. And then I called B the point XY, where we have some x horizontal distance and some y vertical distance. That's the coordinate xy there. Using some right triangle trigonometry, we can figure out that the cosine of alpha, which is adjacent over hypotenuse, is x over c, and the sine of alpha, which is opposite over hypotenuse, that's going to be y divided by c. Or in other terms, x is c times cosine alpha, and y is c times the sine of alpha. So I'm going to go ahead and replace x and y with those things up here for the coordinates for B. And I want to find this distance. I want to figure out what the distance from B to C is. What is the distance of A, right? Very similar to our boat example. We need to figure out the distance of the distance between the boats. Pretend B is a boat and C is a boat. We're trying to find the distance between them. So we're going to use the distance formula. So A is equal to, typically the distance formula is x1 minus x2 quantity squared plus y1 minus y2 quantity squared. Well, x1 is c times cosine alpha, and x2 is b. So we've got c cosine alpha minus b, that quantity is being squared. We're going to add that to y1, which is c sine alpha, minus y2, which is just 0. That quantity is being squared. We're taking the square root of this whole thing because that's what the distance formula is. Okay, so first things first, I'm going to square both sides. And then I'm going to do a ton of algebra. By the way, a minute thing that changed here on this side as well. I got rid of the 0, right? C sine alpha minus 0, that's just C sine of alpha. So then I went ahead and I squared both of these things. And that gave me C squared times cosine squared alpha, right? It's this thing squared. When you square a product like this, you got to square both pieces of it. So that's what happened. And then everything else can be attributed to FOIL method or box method. So this is minus 2bc cosine alpha plus b squared. And then this thing squared is just c squared times sine squared alpha. Okay, I'm going to go ahead and do a little bit of rearranging via some commutative property stuff for addition. And I'm going to rewrite this as c squared cosine squared alpha plus c squared sine squared alpha at the beginning so that I can factor out a c, right? And then the thing that happens here is we get a cosine squared alpha plus a sine squared alpha, which, as we know, is the number 1. So I'm going to go ahead and replace that with the number 1 here. So we get a squared is equal to c squared times 1 plus b squared minus 2bc cosine alpha. And that 2bc cosine alpha has basically just been hanging out ever since we did the FOIL method on this thing. And that is the law of cosines. I went ahead and reorganized it a little bit so that it's in a nice order. A squared is equal to b squared plus c squared minus 2bc cosine alpha. This is really poetic in my mind because this is the Pythagorean theorem. But then you're subtracting 2bc cosine alpha on the other side there. But again, right, and by the way, this is the law of cosines. But again, the thing to keep in mind is that we could have made b the base, right? We could have made b coincident with 0, 0. I mean, this b, not this b. We could have made the vertex c coincident with 0, 0, in which case that would make a the base of this thing. So there's kind of 2 other forms that the law of cosine takes on. Here's the one where we have b as kind of the base of the triangle here. Here's the one where we have, I believe this is a as the base of the triangle. And then here's one where we have c as the base of the triangle. Maybe I have those flipped. It doesn't matter. These are the 3 different versions of the law of cosines. And the cool thing, right? The thing to really notice is that the side is that's opposite its own angle, right? Kind of go on the outer parts of the law of cosines. So if I wanted to write a law of cosines for c, then I know cosine gamma is going to be involved, right? If I'm going to write a law of cosines for a, then I know the cosine of alpha is going to be involved. And similarly, if I want to write a law of cosines for b squared, I know the cosine of beta is going to be involved. And that's what helps me remember what the law of cosines is. It's always side squared is equal to other side squared plus other side squared minus 2 times those other 2 sides times the cosine of the angle that's opposite the side that you have on the other side of the equation. I don't really know if that made sense, but hopefully it did, and hopefully you got something out of that. Okay, let's go back to our example. So we got these 2 boats, right? We figured out that this is a distance of 30 miles. We figured out this is 21 miles. This is 69 degrees, and now we can figure out what this distance is using the law of cosines. So if we get rid of all the detail, all the cool stuff of this picture, we're left with basically this triangle. Right, and we need to figure out what is x. So I'm going to use x squared is equal to the other side squared, 30 degrees, or 30 miles, so 30 squared, plus the other side again, but the other side squared, 21 miles in this case, minus 2 times 30 times 21 times cosine of the angle that's opposite of x. And at this point, it's just a bunch of algebra, right? So this becomes x squared is equal to 900 plus 441 minus 1260 times the cosine of 69 degrees. I'm just adding here. I'm just doing some multiplication here to get this. So we get x squared is equal to 889.46. We're going to square root both sides, and we get that the distance between the 2 boats is 29.82 miles approximately. Now you might be wondering, now hold on, Mock, when you take the square root, you're supposed to have negative stuff as well. True. But that doesn't really make sense in the context of this situation, right? We wouldn't have a negative distance between the boats, so we're basically just throwing that out. We're just taking the principal square root of this thing, so we get 29.82 miles as a positive measurement. All right, so for the second example, we've got an airplane that flies in a triangular course shown in this thing that I drew below. To the nearest degree, find the bearings of the plane while traveling from A to B and from B to C. So I didn't put this on here, but this is like north. This is north. So we need to figure out what this angle is. That's the bearing from A to B, which is nice because it actually doubles as the interior angle of this triangle. So using a law of cosines situation, when we find alpha, we're kind of at the same time also finding the bearing, which is good. The other thing we need to find is beta. right? And again, here's north. So the clockwise rotation away from due north here, we need to go from B to C. This is very clearly going to be bigger than 270 degrees. So we're going to need to do something a little bit different for beta. The law of cosines isn't really going to help. I mean, that might complicate things since it'll give us this angle. Then we need to figure out what beta is going to be from there. But I have a better approach that I'll show you guys after we figure out what alpha is. So if we make this devoid of fun picture stuff, this is just a basic triangle. It's a side-side-side situation, which is a case that's solvable with law of cosines. And I'm going to notice that alpha and 500 are the things that are opposite each other. And so when I'm setting up the law of cosines, I'm going to make it so that it's 500 squared on the left-hand side of the equation and then equals all the other stuff on the right-hand side of the equation, and I know I'm going to end with a cosine of alpha since those outer pieces of the law of cosines have to be opposites. So let's get my picture back in here and start doing a bunch of algebra. 500 squared is 250,000. 410 squared is 168,100. 400 squared is 160,000. And then all this mess is 328,000. Next, I'm going to add these two things, which incidentally gives us something that's extremely close to the other number here. Then I'm going to subtract this thing from both sides to cancel it, which is going to give us negative 78,100 is equal to this other negative 328,000 number, which is fine because when I divide by this negative number, right, I'm going to get a positive here, and that positive number ends up being approximately 0.238. We do need to take an arc cosine of both sides. I wrote it as a cosine inverse, so we get 76.21 degrees. Which, rounded to the nearest degree, is 76 degrees. Okay, so alpha is 76 degrees, which again, like I said before, is also the bearing from A to B. So I'm going to go ahead and record that the bearing of A to B is 76 degrees. So, okay, find the bearings of the plane while traveling from A to B. That's done. Now we just need to focus on from B to C, right? So what's this bearing here? Now for finding beta, the first thing that I am going to notice is that if I draw a theta measurement inside of here, where I've drawn it, then that completes a full revolution, right? That gets us back to due north. So in that case, beta is 360 minus this theta measurement, and theta has an alternate interior angle with vertex C here, right? Because these lines are parallel here. These are alternate interior angles. Alternate interior angles, by the way, is why an angle of elevation is congruent to an angle of depression, which these aren't really, I wouldn't classify these as angles of elevation or angles of depression. It's kind of like an overhead view that we're looking at. But they are alternate interior angles, and so we know that they're congruent. And the cool thing is, if I want to figure out what this theta measurement is, which again will give us this one, which is good, because then we just subtract it away from 360 to figure out what the bearing is, we don't have to use a law of cosines now that we have an angle. Instead, we have a situation where we could utilize the law of sines. So I'm going to set up the law of sines using the linked pair 576 degrees, right? Pretend there's a chain, right, that's going along here. So that's the known ratio. The one that we don't know is the sine of theta over 400. So to solve this, I multiplied both sides by 400 whilst also simplifying, because there'd be a 400 here. I divided both sides by 100, like top and bottom is what I mean. So that just became 4/5. And then to find theta, I just need to take a arc sine of both sides. So I just stuck all this in this mess into my calculator. I got 50.9 degrees, which again, rounded to the nearest degree, is 51 degrees. So since this is 51 degrees, this is also 51 degrees. And as we know, the first thing we noticed about beta is that it's 360 minus this theta measurement, which we just found is 59 degrees, which means beta is 360 degrees minus 51 degrees, or 309 degrees. And that is the end of the problem, right? The bearing from B to C is 309 degrees. Okay, so just a couple of quick examples for this video. This one was a side-side-side situation. The first one that we did was a side-angle-side situation, both of which can be solved via the law of cosines. Hopefully this video was helpful. If you have any questions, please leave them in the comments section below. Thanks a ton for watching, and I'll see you in the next one.